6.1 Introduction to Vectors. Vectors are used a lot in physics as far as forces and energy working on an object, and the direction is specific as well. So gravity, for instance, has a downward pull, and it has a magnitude, the strength of its pull. So it could be represented by a vector. Pilot needs to set speed and direction of their flight, etc. Lots of other applications. Before we get into what a vector is and how to use them, we want to compare it and contrast it to a scalar. So we're going to have two words here. First one is scalar. This is a quantity that describes magnitude only. Magnitude only, so not magnitude and direction, just magnitude. It can be with or without units, but we want to say it does, maybe, does not include direction. So something like, I took 5 steps. That would be a scalar measurement of 5 steps. Or I drove 100 kilometers today. Okay, it doesn't tell you what direction you drove in or where you went. It's just a quantity that describes the magnitude. It's a scalar measurement. Then we have vector. Vector is a quantity that has magnitude and direction. So now if we said I took 5 steps to the left, that's a vector measurement. It tells you where the 5 steps, the direction of that magnitude of 5 steps to the left. Or I drove 100 kilometers north, that's a vector. 100 kilometers is the magnitude and north is the direction. It has to have both of those. If it has both of those, it's a vector. If it's just magnitude, it is a scalar measurement. So there are a handful of, we can make a little chart of examples. Maybe let's do that. So, we'll just head into example 1. So example 1 just says state whether each of the following is an example of a vector or a scalar quantity. If you want to do this, you can do that on the handout that I've given you, or I'll probably jot them down here as well and walk through them. So example 1, we're just determining if it's vector or scalar. So all we need to know is if it has magnitude and direction or just magnitude. Number A says a car traveling 50 kilometers per hour east. Vector or scalar?
Vector.
Why?
Because as the direction east.
Yeah, it has magnitude and direction. Let's just do these orally. B, a child pulling a wagon with a force of 100 newtons at 30 degrees to the horizontal.
Also a vector.
Also a vector, okay? So we have in there a little introduction to that force is measured in newtons and represented by capital N. And then you also have a different way of measuring direction, 30 degrees to the horizontal. And we'll talk about those things as we move along. We don't need to have them specifically now, but B is vector. C says a man's mass of 88 kilograms. Scalar. Could you have a, could mass even be a vector? Can you be a certain weight in a certain direction?
I guess you can represent it at 88 as a quantity.
Yeah, so it is a quantity, but it's a scalar quantity because there's no direction included.
Yeah.
Good. D, a woman skiing at a speed of 25 kilometers per hour. Scalar, and it's, notice that it's speed. If it were a vector, it would have direction, and then that would be velocity, not speed. So speed is a scalar measurement. A parachutist falling 20 kilometers per hour downward.
vector.
So there we have an example of speed with direction, meaning it's actually velocity. F, acceleration due to gravity on Earth is 9.8 meters per second squared downward. Vector, and there we have acceleration. A, B, C, D, E, F, G. The number 5. I don't even know.
Guess it's a scalar quantity.
Yeah, it's scalar because it has no units. It's okay if it has no units to be a scalar. So anything that's just a number or a value, as long as it doesn't have direction, it's scalar. So G is scalar. A, B, C, D, E, F, G, H. Your weight on a bathroom scale.
Scalar.
It's a tricky one.
Well, your weight is scalar, but because it's on a bathroom scale, you can say it's a vector.
How does the scale measure your weight? Gravity pulling down on you. So that's a bit of a tricky one. The scale uses the downward acceleration of gravity in order to calculate your weight. So that is a vector. There's a little note here that says your weight in newtons is your mass in kilograms multiplied by the acceleration due to gravity. So everybody's weight, the force that our bodies impose on the ground, can be measured in newtons. And it is our mass multiplied by 9.8 meters per second squared downward. Although your mass remains constant, your weight would be different on another planet because gravity is different on other planets. So your scale, if we brought our scale to Mars or to the moon, our weight would be different, whereas our mass would remain constant. Our mass would be the same. Anyway, that's example 1. Let's take some more notes. Okay, you know what vectors are now. We're going to talk about how to represent them. Representing vectors. And there's a handful of different symbols, words, or images that can be used to talk about them. So the first thing that we're going to talk about is using words. Using words, we just give an example. You could say something like 5 kilometers at an angle of 30 degrees to the horizontal. So that comes from example 1. That was one of the things that we talked about. 30 degrees to the horizontal. Anyway, that's just how you would write it in words. There's also a diagram that you can use. In a diagram, which is called a geometric vector. So there's a bit of a hint that we're going to be working with geometry and figures, triangles and parallelograms, etc. And it's basically just a representation of a vector using an arrow diagram or a directed line segment, and it's going to show magnitude and direction. So in a diagram, it's an arrow that shows magnitude and direction. And the length of the arrow is proportional to the vector's magnitude. So if you're just drawing one vector, one arrow, this sentence is kind of irrelevant, but if you're drawing multiple vectors on a single diagram, then the length of arrow is proportional to the vector's magnitude. Okay, so I'll draw a diagram, and we're going to use the same example as we did up here in words. So I'm going to draw the horizontal. Horizontal is just a horizontal line, straight line. and we're saying we're going 5 kilometers at an angle of 30 degrees to the horizontal. So here's 30 degrees from the horizontal to our vector, and we have a magnitude of 5 kilometers. We're going to note that it comes from A to B. So here A is called the starting point or the tail, and B is the end or terminal point, or also called the tip or the head. And we can say that this is the tail, this is the tip or the head, or the end or the terminal point, whatever we're going to use. And maybe we should note that this is the horizontal. Okay, so again, what do we have? We have direction, and magnitude. Okay, then we can use, so we've got words, diagrams, and in symbols. There are a couple of different ways that we use symbols. One of them is just using kind of a line segment or ray notification. So this is vector AB, which would be like this. Vector AB, okay? This little arrow indicates that it's a vector, and it's the vector that goes from the starting point A to the end point B, from the tail to the tip. There is another way that we use it in symbols. Instead of representing it by its endpoints, you can also just represent it by, you can name the side. So it's just like triangles really, but we can call this, that's a cursive V right there. I don't know how to do a cursive V, something like that. And it's just going to have a little arrow over it. Okay, so that is the vector. Now, sometimes we just want to talk about the magnitude of the vector and not its direction. So if you just want to talk about the magnitude, which is like the size or size of the vector. So again, we're not talking about direction, which means that this is going to be related to the concept of an absolute value. So the magnitude of the vector is denoted using the absolute value notation or symbol. So vector AB has magnitude of the absolute value of vector AB. Vector V has the magnitude, the absolute value of vector V. Essentially, when you're talking about magnitude, you're talking about the vector without consideration for the direction that it's heading in. So whether it's positive, negative, left, right, 30 degrees, 90 degrees, whatever, the magnitude of it is all that's important. Then you're going to use the absolute value notation there, where sign doesn't matter. Okay, that's just dealing with magnitude. So this is representing vectors 1, 2, 3 different ways. Then we have a note on magnitude, and I'm going to clear my board for some notes on direction. Okay, vector direction can be expressed using several different methods. We'll just go like that, and we'll say the first one is the true bearing. True bearing. This is a compass measurement where the angle is measured from north in a clockwise direction. So for a true bearing, the angle is measured from north in a, and I'm stopping here because I'm going to use a little diagram on my right side here, in a clockwise direction. So if we have a diagram here and it looks like a compass and we have north, you'd have north, east, south, west, but we're not going to write all those in because in this case we're just concerned with where north is. So we're always going to refer to our angles with respect to north. And so if we had an angle of, let's say, 40 degrees from north, okay, this vector right here would have a bearing of 040, or 40 degrees from north. It's always measured clockwise from north, okay? So we could do another one. Let's say, let's go over here. So you might be tempted to head counterclockwise here. Don't do it, okay? We're going to go all the way around from north, past 270 to 280. So that would be 280 degrees. Okay? So they're always expressed using a 3-digit number. Use a 3-digit number. And so you'd have, you know, north would be 000 degrees. And east would be 090 degrees. South would be 180 degrees. Okay, over here would be 270 degrees. And again, always measured clockwise from the direction due north. And this often you just use the word bearing. So if a ship is traveling at a bearing of 50 degrees, you know, you just, okay, from where the ship is, you draw your north line and you go 50 degrees clockwise. Okay, and that's the direction that it's heading. And then if you had the magnitude or how far it's heading in that direction or the location of where it's trying to go, then you would have a vector. Okay, the other one is a quadrant bearing. So this is true bearing. And now we have quadrant bearing. So again, similar, but this time you can refer to any of the directions on the cardinal on the compass. You can refer to north, east, south, or west. So it is a measure a measurement between 0 degrees and 90 degrees east or west of the north-south line. So we'll explain that in a minute, but you can head east or west from the north-south line. So if I draw my vertical line over here on my compass, that is the north-south line. Okay, compass generally just has an arrow pointing up for north. Okay, there's south. And here's my east and west. Never eat shredded wheat, never eat soggy wheat. And so I could draw an example here. Let's say we go from north and we're heading west at an angle of, let's say this is 35 degrees. then the example that I've drawn would be, this is maybe a blue. I'll say that this is north 35 degrees west. So if you have north, with respect to north, you're heading 35 degrees west. Okay, we could do another one. Different example here. What about this example here? Let's say I take a hard angle like this. Okay, from the north-south line, so we'd have south. This is looking about 80 degrees east of south. So you'd have south, 80 degrees east. So you're starting, heading south, looking down this line, and then you're going to from there head 80 degrees to the east. Then the bearing, the quadrant bearing of this vector, is the direction of it is south 80 degrees east. All quadrant bearings are referred from north or from south to east or to the west, if that makes sense. So either north or south is always, N or S is always going to be your first letter, and E or W is always going to be your second letter, and in here it's always going to be between 0 and 90. Good? Let's test out a few examples here. Example 2, we are going to describe some vectors. Example 2, describe them. I'm going to draw them quick because future listeners might not have the examples printed for them. So there's our horizontal, and we have an angle here of 110 degrees. And we're told that the magnitude is 14 centimeters from P to Q. What can we say? Well, PQ is, we're just describing the magnitude and the direction. So according to the picture, we have a magnitude of 14 centimeters at 110 degrees, and that's relating to the horizontal. So I guess we should have actually talked about this in our way of expressing well, I guess this has direction and magnitude, but the direction here is with relation to the horizontal. We didn't put that in our two examples or in our two ways of expressing direction. It's in the main diagram, but it's not in the little subsection of notes on direction.
Yeah, you wrote a note and you said inwards, put distance at an angle of degrees to the horizontal.
Yeah, so it's in there anyway. So you can describe it using true bearing, quadrant bearing, but here it's clearly related to the horizontal as a third way of doing direction. Okay, B. B looks like this. We've got north, east, south, west, and we have a picture showing a vector coming out this way. It's called vector U. We're told it is 2.3 kilometers, and we're given the angle from the north clockwise is 135 degrees. So this is using a true bearing. It's not a number between 0 and 90, so I know it's not a quadrant bearing, and it doesn't tell me the direction that it's heading to. It just gives me a 3-digit bearing from north. So this is a true bearing, 2.3 kilometers at a true bearing of 135 degrees. This little word at is the connection between the magnitude and the direction. All right, last one is another drawing that indicates north, but it also indicates east, south, and west. And then we have vector V coming out here with a magnitude of 9.8 newtons, and the direction is given to us from south. We're heading toward the west at an angle of 35 degrees. So now we do have a quadrant bearing. And again, we're going to put our magnitude first, 9.8 newtons at a quadrant bearing of, start with our north-south line. So we're heading south, and then from south, we're heading 35 degrees toward the west. All right, so one example of each type of diagram, always with the magnitude and the direction. And we've indicated what we're referring to. The direction here is related to the horizontal, then it's a true bearing, then it's a quadrant bearing. All right, in example 2, we were given diagrams and we explained them. In example 3, we're going to be given an explanation and we're going to draw it. So this is drawing vectors. And we are told that vector v is 2 kilometers. Vector v equals 2 kilometers at a bearing of 0 to 0 degrees. I mean, it tells us it's at a bearing of, so we're looking at true bearing. We're coming from north, so I'm going to just draw my diagram with my north and then my east-west line as well. And we're told that we're coming from north 20 degrees. So that's going to look something like that. And again, I'm only drawing, we said the length of this arrow has to be proportional to the magnitude of the vector. I'm only drawing one vector in each diagram, so I don't need to worry about that too much. And this is 2 kilometers as a magnitude, and the direction here, the angle here is, and I'll just write it maybe on this side, 20 degrees, right? That's right there. And I guess, so one thing they put in here is also a scale, like a conversion from length on my paper to the 2 kilometers. So we'll say I did this in centimeters, and this is 1 centimeter, 2 centimeters. So they actually want us to say 1 centimeter is 1 kilometer in real life. So 1 centimeter on my diagram represents 1 kilometer in real life. All right, B, I'm going to come over here. B tells us that vector V is equal to 4 kilometers at a bearing of 295 degrees. So again, we're looking at a true bearing diagram. We've got north at the top, and from north, we're heading clockwise at an angle of 295 degrees. So I go 90, 180, 270, and 25 more. It's going to maybe look something like this. And I'm going to use the same scale. 1 centimeter is 1 kilometer. And then we are going to be able to see that in comparison to our example 3A at 2 kilometers, this one should be about twice as long. 1, 2, 3, 4 centimeters, which is 4 kilometers. And I neglected to do this in my first one, but we need to name our vector. So put the name typically near the tip, near the end. They're both vector V. And just to show what we're doing here, we're coming from north clockwise all the way around, 3-digit number, 295 degrees. C, vector U is equal to 30 kilometers per hour at a quadrant bearing, of north, and maybe I will make it fit here, north 40 degrees east. So I'm going to whip out my compass. North, this time I'm in a quadrant bearing, so I'm going to put all 4 of my letters on here, north, east, south, west. We're heading from north, we're going to go 40 degrees to the east. Looks something like that, right? 40 degrees. This is vector u, and it is represented by a magnitude of 30 kilometers per hour. And we're going to add a scale to this as well. So when you're drawing these, you'll have a little ruler out, and you'll make sure that your scale actually matches what you're saying. 1 centimeter in my diagram is 10 kilometers per hour. That's going to get too cluttered there. 1 centimeter is 10 kilometers per hour. Good. One more in this section. D says vector u is equal to 40 kilometers per hour at a quadrant bearing of south 70 degrees west. So again, I'm going to draw my compass. North, east, south, west. This time we are from the south heading toward the east at an angle of 70 degrees. It's going to look something like that. I'm going to use the same scale, so I'm just looking back at my length of my line, my vector in part C. I'm going to use the same scale, so this should be a little bit longer. I'm going to name my vector over here at the tip. It's vector u. We're heading from south at an angle of 70 degrees. And the magnitude is 40 kilometers per hour. My scale again is 1 centimeter. In my diagram is equal to 10 kilometers, represents 10 kilometers per hour in real life. There you have it. Nothing too challenging. Just be aware of what you're measuring from, if it's a true bearing or a quadrant bearing, or we didn't do anything here from the horizontal, but I suppose you could have that situation as well. And use your scale, show your angle and your magnitude, and name the vector. Same up here, scale, direction, and magnitude, and name your vector. All right, we know all about vectors, the magnitude and the direction, the diagrams, how to record them using symbols and words. Now, how can vectors relate to each other? And again, we said we were going to get into some geometry, and so some of these terms are going to be really familiar. The first one is parallel vectors. Okay, a parallel vector, I mean, you could probably write the definition yourself. Parallel vectors have same or opposite direction. Same or opposite direction. Do you think magnitude matters?
Nope.
Okay, let's just write it that way. Magnitude does not matter. Okay, so examples of that just really quickly. Here's a vector, here's a vector. Okay, they're heading the same direction. They have different magnitude. What about, there's a vector and there's a vector. Okay, it looks like they have same magnitude, doesn't really matter. I can actually just make that one longer, so that is deliberately not the same, but it has opposite direction. So these guys are parallel as well. Okay. Then we have equivalent vectors. And they have the same magnitude and same direction. Same magnitude and same direction, but that doesn't necessarily put them right on top of each other because location doesn't matter. Location does not matter. Okay, so if you're working in a diagram or on a plane and you have a vector that looks like this, and then somewhere else you also have a vector that has the exact same direction and the exact same magnitude, then these guys would be equivalent. All right, and then you have opposite. After we're done this, I'll draw a diagram to explain them a little bit better. But then you have opposite vectors. Opposite vectors have the same magnitude, but opposite direction. So if you were going to add opposite vectors, you'd get 0. You'd get the 0 vector. Same magnitude, opposite direction. Again, the location does not matter. Location does not matter. And how would we write them? Well, the opposite of AB, vector AB, is negative AB, negative the vector AB. So an opposite, that would be something like this, heading this way. And again, location doesn't matter. So I'm just going to make them look like they're the same direction and same magnitude. These two vectors would be opposites. Okay. I should be kind of naming my vectors in the diagrams, but I think you kind of understand. These guys belong with that term, these guys belong with that term, and these guys belong with that term. Hopefully that didn't just make it more confusing. I'm just going to quickly draw a couple of examples that we can talk about. So if I draw a trapezoid, PS QR, then what do we have? What's the relationship between PQ and SR? Parallel, equivalent, or opposite? Okay, vector PQ is parallel to vector SR, and you can write it the other way. SR is parallel to PQ. Both of those things are true. What if we had a parallelogram? A, B, C, D. So in our first one, in our trapezoid, PQ and SR were parallel, but they were not equivalent. Okay, but here in our second one, we do have an example of equivalent vectors, and we can say AD, vector AD, is equal to vector BC. Okay, again, location does not matter. Because they have the same magnitude and the same direction, they are equivalent. We could write BC equals AD. We also have in our diagram that the vector AB is equal to the vector DC. And also, we could flip that around and say DC is equal to AB. And one other thing that we might want to note in this section, so in this, using this same example, because AD is equal to BC, it's also true that AD, that is equal to, so if we looked at this vector backwards from C to B, then AD is equal to negative CB. Okay? So the vector CB, if we looked at this from C to B, then that would be an opposite vector of AD. Okay, we can do the same thing with this example here. If we look at AB from A to B, the vector, well, the vector from C to D is an opposite vector. So AB is equal to negative the vector CD. Okay, so you can look at vectors from either way. It is important which letter you put first. That will tell the direction of the vector. So you don't want to call a vector its opposite. Okay, let's apply this in example 5. Example 5, we're talking about equivalent and opposite vectors. Equivalent and opposite vectors. And in A, we're given a diagram of a vector, a picture of a vector, and told to draw a vector equivalent to it. So it is what it's as easy as it looks. There's vector AB. We have the tail and the tip, and we need to draw vector EF, and it has to be equivalent. So equivalent means location doesn't matter, but it does have to have the same direction and the same velocity. And the same magnitude. So at this point, I'd probably make sure I had a ruler out. And that's 2.5 inches on my thingamajig here. So I'm going to make sure I go the same direction. And I start here and go 2.5 inches in order to make sure that I have, and I got to name it from E to F. So now I have EF is equivalent to vector AB. In example 5b, we're going to write an expression to show how AB and EF are related. Well, we're told that they're equivalent and we drew them equivalent. So all we really need to do is make sure that we are writing from start to end, from the initial point to a terminal point. And same thing with our second vector from E to F. Because they have the same direction and magnitude, we can use that equal sign. They are equivalent. C says, draw a vector opposite AB. Draw a vector that is opposite to AB. Again, this doesn't matter where it is, but it has to have the same direction. Sorry, opposite direction. So I'm going to draw the same kind of line and just put my arrow on the other side. And I need to make sure it has the same magnitude, which was 2.5 inches. So I'm going from here, 1, 2.5. This time I'm just going to put the arrow here. And I'm going to make sure that we're supposed to call it GH. So I need to make sure that my G is up here, my H is down there. And then D is to write an expression to show how AB and GH are related. We use the notation that we did just in our notes there. We have vector AB is equal to the opposite of vector GH. They have the same magnitude, but they are opposite directions. That is all for 6.1 Introduction to Vectors. Your practice problems are on page 310. They are numbers, you should be able to handle 1 through 14.